We've done a bit of descriptive chemistry of the main group elements, specifically this one, which is the halogens, and this one, which is group 2. But what we've said very little about are these ones in the middle here, which are the D block elements. And that's the purpose of this set of lessons, because this is one of the major topics that you do have to know about for your A-level. So that's really what we're going to look at here. So the first thing is to remind yourself how electron configurations work. So if we return to the periodic table, remember the way it works is that as you go across the top, you're filling up 1s, so we get to 1s2 at that point, and then continuing across here, you get 2s1, 2s2, and then 2p from 2p1 through to 2p6, and then 3s1, 3s2 through to 3p6. And it's what happens in this fourth row that gets complicated, because remember, in the third shell you've still got 3d orbitals that haven't yet been filled up, but before you get to those you come back to fill up 4s. So these two elements, potassium and calcium, you have 3p6, but you now have 4s1, 4s2, and that happens simply because 4s is lower in energy than 3d. So although it's a lower shell number, 3d has higher energy than 4s at that point. Once you've filled up 4s, now you start filling 3d. So as we go across here, there are 10 elements from scandium through to zinc, and that's because there are 5 orbitals in 3d, 2 electrons in each orbital. So essentially what we're doing is filling up 3d as we go across here, and then we're back in the p block, and so we're filling up p orbitals again, and this is where 4p gets filled up. So gallium will be 4p1, germanium will be 4p2, through to krypton, which is 4p6, and that's the limit of what you need to be able to do in terms of writing electron configurations down. So for these elements in the D block, it ought to be fairly straightforward to write down what their electron configurations would be, because you just count how far across in the D block you've got, and that should tell you how many D electrons there are in the 3D subshell. So scandium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then you've got 4s2, and then it's 3d1, and titanium is 3d2, and vanadium is 3d3, and so on. However, there are unfortunately 2 of them which don't fit the trend. So if we look at chromium, which is here, it's the 4th one across, so the prediction would be that it should be 3d4, 4s2. But actually, for reasons that you don't need to know anything about, and which actually are quite subtle quantum mechanical reasons, so it's just as well we don't need to know them, chromium has an odd configuration. It borrows 1 electron out of 4s and adds it into 3d, so it's actually 3d5, 4s1, rather than 3d4, 4s2. So you just have to remember that chromium is odd. It just has 3d5, 1 more d electron than you'd expect, but at the price of only having 1 in 4s, so 3d5, 4s1. After that it goes back to what you'd expect. So manganese is the 5th one across, 3d5, 4s2, iron's 3d6, 4s2, and cobalt and nickel again are what you'd expect, but copper does the same thing as chromium. So copper is odd because again it borrows an electron from 4s and moves it into 3d. So instead of being 3d9 as we'd expect, it's 3d10, 4s1. and then zinc goes back to the normal pattern, so it is the 10th one across, so it's 3d10 and 4s2. Okay, so just need to remember really that for most of them you can simply use their position in the D block to work out how many D electrons are there, but that chromium and copper are bizarre. So that's just a reminder of that. So the next thing you need to worry about is what happens when you form ions. And again, this is not what you would expect if you just think about it logically, because what we've seen is that in general you put in 4s electrons and then you start adding 3d electrons. So since they were the last ones to be added, you would probably expect that the 3d electrons would be the easiest ones to remove. But in fact it doesn't work that way. What actually happens is that you always, and this time there are no exceptions to the rule, you just always remove whatever 4s electrons there are first, and only then do you potentially start losing some 3d electrons as well. And the thing that's characteristic of transition metal ions is that because the energies of 3d and 4s are very similar, it's quite possible to lose variable numbers of 3d electrons in addition to the 4s ones. So it gives you a couple of examples here. Titanium has the atomic configuration that we'd expect. It's the second one across in the series, so it's 3d2 4s2 when it's an atom, and when it forms an ion you lose the 4s electrons first. So if it's just Ti2+, it just loses those 4s electrons and the 3d ones are still there, so the highest energy electrons 3d2. Here's cobalt, which is an example. So we've got 3d7 4s2 as an atom, and now we're looking at cobalt 3+ ion. So to achieve 3+, you first have to remove those two 4s electrons, but then you have to remove one of the 3ds as well. So you've lost 3 electrons altogether. So what you end up with is you still have 3d6 rather than 7, and you've lost the 4s. Again, the reason why 4s is lost first is not something you have to explain, but it just has to do with the fact that the order of energy levels of electrons in the ion is not the same as it is in an unreacted atom. But you absolutely don't have to explain that. It's just a case of memorizing that you always take away the 3d electrons first. So they're very likely to ask you electron configurations either of atoms or of ions, and you need to remember those rules for doing those things. So the term transition element rather than D block element refers to largely the same group of elements, but not quite. So the definition of a transition element, which again you need to know, is that it's an element that has one or more stable ions with an incomplete D subshell, and by incomplete it means that it has at least one D electron but fewer than 10, so it's not empty and it's not full. So something can only be classed as a D block element if it has at least one ion that has between 1 and 9 D electrons, and that doesn't quite include all of the transition elements. So the two exceptions that again you need to be aware of are scandium and zinc. So scandium is the first element in the D block, so the atom is 4s2 3d1, and what happens is that scandium only ever forms 3+ ion, so its only stable ion is scandium 3+, and of course that means it's lost its 3d and it's lost its 4s, so it doesn't have an incomplete 3d subshell, it has an empty one, and because that's the only stable ion, it doesn't count as a transition element. Zinc is the other one, because zinc as an atom has a full 3D subshell, so it's 3d10 4s2, and its only stable ion is 2+. So it loses the two 4s electrons, but it still has a complete set of 3D electrons, so it's 3d10, and therefore again it doesn't qualify because it doesn't have an ion with an incomplete 3D subshell. So this is a really annoying definition, and you just have to know that it's not quite the same set of elements therefore as the D block. And they will sometimes ask you, why does zinc not count as a transition element, and that's what you have to say. But there is a certain logic to it. It's not just a completely random new definition that they've come up with, because ions that have an incomplete 3D subshell have characteristic properties that mark transition elements out as different from other ones. And what you find is that scandium 3+ and zinc 2+ don't have those unusual properties, and that's why they get excluded. So let's just briefly summarize what those characteristic properties are. Before you do that, sorry, I forgot we were going to do this. Before you do that, it would be a good idea to do questions 1 to 3 from the question pack, which are just the electron configuration questions. So have a go at those, and then we can look at these characteristics. So here they are. If they ask you what are the characteristic properties, these are the 3 you have to give. You might well be able to think of other things that you think are typical of transition elements, rather, that make them different from other elements. For example, they're better for making, for building bridges than elements in the main groups. If you tried to make a bridge out of sodium or oxygen, you can see that would probably not work very well, whereas transition elements are quite good for that kind of thing. But they won't accept those, so you have to give these as the characteristic properties. And we're going to explore each of them a little bit more. So variable oxidation state is this idea that if you take iron, for example, it doesn't always exist as Fe2+, it can exist as Fe3+, and compounds of both of those are very common. And some transition elements can exist in a whole bunch of different oxidation states. The second is this catalytic activity. If you think of the catalysts that you've learned, in various reactions so far, some of them are acids, like in esterification, you use sulfuric acid, but most of them otherwise tend to be transition elements. So for example, nickel in addition of hydrogen to alkenes or nitriles, and sometimes they're transition metal compounds, like iron 3 chloride in Friedel-Crafts reaction. So this catalytic activity of both the metals and their compounds is something that's a very important feature of transition elements. And the third is that where sodium compounds or your main group compounds like that generally don't have any color unless the negative ion has a color to it. Transition elements typically form colored compounds, and the color originates from the ion with its incomplete D subshell. So for variable oxidation state, as we said, the reason they can do that is because the energies of 4s and 3d electrons are very similar. So having removed the 4s, it's not then a huge leap in energy to start removing 3d as well. And you just need to be able to exemplify that if they ask you, how is this illustrated? So for iron, for example, Fe2+, Fe3+, as we've said before, are both very commonly encountered. So you could give examples like iron 2 hydroxide, iron 3 hydroxide as being both compounds that are easily formed, and we'll look at those in a later section. And you can write down what the electron configuration of the Fe2+ and Fe3+ ions would be. There are also higher oxidation states accessible to many transition elements, but what happens is that if you're above, say, 4+, at that point the ions the transition element doesn't exist as an ion alone. It becomes covalently bonded to usually oxygen, could be other elements, but most commonly oxygen. So you've come across, for example, ions like manganate 7, MnO4-, or dichromate, Cr2O7-2-, where you have very high oxidation states. And in those, it's important to know that those elements don't exist as Mn7+ ions or Cr6+ ions. That's not energetically feasible. They exist in those high oxidation states, but they're then covalently bonded to oxygen atoms. And iron has an example of one of those too. FeO4-2-. If you work out the oxidation state, the ion is +6 in that ferrate-6 ion. Catalytic activity, again, often is related to the ability to switch oxidation states, but that's not the only reason. Mainly, you need to be able to give some examples. So we've already mentioned this one, which you know from the organic chemistry that we've done. So you can use nickel actually for both of these reactions. It says platinum there, which works better but is too expensive to use normally. So actually nickel's used for both those additions of hydrogen. And Friedel-Crafts we've mentioned as an example of a compound, again, that you're familiar with. So it's a very important process thing industrially, because catalysts, remember, first of all, reduce the amount of fuel that is needed for industrial processes because they can operate at a lower temperature. So that's good cost-wise, but is also good for the environment because it means less greenhouse gases being added to the atmosphere. And catalysis often makes reactions possible to use which otherwise would just be so slow you couldn't use them at all. And that allows you, for example, to use processes with a better atom economy. So again, it's environmentally good because you use up raw materials less quickly if you have higher atom economy in your process, and having a catalyst to make the key reactions feasible is often a reason for that. You know why that has been opened up as a possibility. Finally, then, coloured compounds. The origin of the colour is really quite an interesting story, but is beyond A level. So you just have to know that it's linked to having a partially filled D subshell. So if you have a D0 ion or a D10 ion, it won't be coloured. And that's important to realise that. But anything that has at least one but fewer than 10 D electrons, you'll expect to be coloured. And unfortunately, there are quite a few colours that you have to learn specifically for the purposes of this part of the A level.